Whoops. All right, welcome back to, wow, I forgot how this works. Welcome back to operating systems. So, our last lecture, we're pretty much done. So, we have more review today, which is again an ask away. So, is there any pressing questions from anyone sitting here already? If not, the Discord was like maybe some condition variables, maybe some more threads, maybe some socket stuff. Go do that CS111 exam. So any preferences? Yep. Condition variables. What about condition variables? Explain them from the beginning. All right, so I made this up with the other section, so I will do that for you. So let me erase something real quick. All right, remember this question that we took up last time that had, we were trying to make it such that only thread 0 ran this initialize everything function before any other thread executed, then every other thread can execute their own individual initialize thread function. So, do we all remember that? All right, well, if we want to do condition variables, how would, oh, yeah.
Oh, are you asking for how would you deal with condition variables?
Yeah, how would I do this with condition variables?
So if thread 0 initialize everything, in the else, with practically the same thing as thread yield, you'll do condition wait. You'll do condition wait, of course. You need the mutex before, you need to lock. You need to lock before, where would you need to lock that? I don't know where you need to lock, but instead of thread yield, you use the condition wait, and then after initialize everything, you can just do condition broadcast.
Yeah, so remember about condition variables. Let's see. Condition variables are basically just one big queue. That's what the condition variable is, and you need a mutex with it, and then you need some condition that you are actually waiting on. So for this, the condition I will probably have is something like I want a Boolean that just says is initialized, and initialized is currently false, and I'll have thread 0 change it to true whenever it's done. What is that high pitch? Is it that? Am I the only one that can hear the high-pitched noise? Okay. Yeah, maybe if I'm like, yeah, maybe if as soon as I hit like 50 or 60, I can't hear it anymore, and I'll be a lot happier. All right, so our condition variable could be like a bool is initialized. And then I'm just gonna not write pthread whatever in front of all these. So I'll have my condition variable, I'll just call it cond because I'm creative, and then I'll have a mutex called mutex because again, I'm super creative. So those are everything I need for condition variables. And for my condition variables, there are two functions that we learned and then one that you already said that would probably make more sense in this case. So I have cond wait, and then cond signal. And cond wait with the condition will essentially put this thread to sleep, block it, and also unlock the mutex associated with it until some other thread wakes it up by calling signal on that condition variable. So anything else you want me to explain about condition variables? Those are the two basic things we have. Yeah?
Would it not make sense to use broadcasting this?
Yeah, it would. We'll get to that. Yeah?
Could you explain again why mutex?
So you need a mutex because it's assumed that when you call wait, you have the mutex acquired because, well, you're waiting on a condition variable that other threads can change, so you don't want data races, so you'll need a mutex anyways. And as part of the wait, it needs to unlock the mutex whenever it puts itself to sleep so another thread can get the mutex, make some progress, hopefully change the variable to true or whatever I'm waiting on, and then wake me up. And then I would have to reacquire the mutex so that when I return, I know I have the mutex and don't have any data erases. Yep. Yes, it is technically undefined behavior if you call it without locking the mutex beforehand. It will, yeah, because they assume it should be locked whenever you have it. So, in order to implement this, I could essentially leave my if statement, and then here, right after initialize everything, I could have a call to, I'll just shorthand it, call the lock. Oh my God, that is so annoying. Okay, have it called the lock with that mutex. Then after I acquire the mutex, then I can go ahead and change that is initialized variable. So I'll just shorten it to isInit equal to true. And then in this case, well, I could, doesn't really matter, I could unlock the mutex. And then in this case, I told you to only worry about signal. But in this case, I might have multiple threads going to sleep as soon as because essentially if threads 1 through 7 have run first, they should be waiting. So I might have up to 7 threads asleep. In this case, I want to wake all of them up because they could all continue as soon as I have initialized everything. So even though we said we did not cover it, if I asked this particular question, which you would not get, broadcast would probably be more appropriate because I could have multiple threads waiting. But instead of broadcast, since I know the number of threads, I could have a for loop that calls signal like 7 times if I want. That would also be a valid solution, but broadcast would probably be the better thing to do. All right, so that is all of the code that would go essentially right here. So now instead of thread yield, I probably do something like while cond, actually, well, first I need to lock the mutex. Then after I lock the mutex, I can check the condition, which the condition is actually the Boolean. So I would do while not is init. Then if currently is initialized is false, that means this thread should be put to sleep because, well, the thread 0 hasn't executed yet. So here is when I would call a cond wait on that condition variable with this mutex. And then that would just be in a while loop. Now, after I break out of the while loop on this line right here, I am guaranteed that is initialized is equal to true because I still have the mutex and, well, I still have the mutex and I was woken up and I'm guaranteed that it is true. So now I can go ahead and just unlock and then just fall through and then run my initialized thread. So unlock. Something like that. So any questions about that? Yeah. Oh, go. Yeah. Go ahead. Yeah, so condition wait will like atomically put this thread in the queue, put this thread to sleep and also unlock the mutex. And then whenever it's woken back up, it will try and reacquire the mutex before returning. Yep.
So the cron T variable is you said it's a queue. Does broadcast basically like fill the queue? Is that what it's doing?
Yeah, so like the condition, way I like to think about it is the queue. So broadcast on it will wake everything up that is currently in the queue. Yep.
Why do we use the while loop within it, isn't it? If like, if we wait on the threads, won't they just like go to sleep? And you just need to wait for broadcast until they wake up?
So like if I just change, so common thing is like, hey, what happens if I change this to an if instead? So
What happens if another thread somehow changes the variable again? You can only check it once.
yeah, so in this case, maybe it's technically okay because they just go to sleep and then get woken up once. I only change it in one direction. But if you actually read the spec of condition wait, you can actually get woken up at any time, even if someone doesn't signal you, technically, I believe. So you could get woken up, and then you would have to be responsible for rechecking the variable anyways. If I just have it in an if, I won't recheck it again. I'll just assume that's true and then fall through. So common thing is always put your checking of the variable in a while loop, because then you're guaranteed no matter what, you are always rechecking the variable and you are always sure it is up to date and you are not in for a surprise. In this case, it would probably work, but in general, probably is not a good solution because, well, if you change this later and have another thread, wake up the other threads on the queue, it's just not going to work anymore. You're going to be surprised. Yeah.
I guess no reason not to use a while loop, right?
Yeah, no reason not to use a while loop. Yep.
Why do you lock the isn't it equals true and unlock it? Like, since the only thread that can do that is thread 0, why do you need to lock it? You check the thread ID.
So why do I need to lock it? So if I don't unlock it, technically I have a data race because other threads could be reading it while I am writing it. So in this case, if I just don't have it, even in this case, sometimes it's okay not to have it, but even in this case, this could lead to very bad things. This is actually a good exam question. I wish I put this on. So what bad thing happens here if I don't have this lock?
If it changes it while.
If it changes it while reading?
Well, I mean, like, if it reads right before it gets changed.
So if it reads right before it gets changed, so what's another color?
Wouldn't it just fall through the whole thing?
So thread 2 reads it. It's currently false. Yeah.
So basically thread 2, it checks it while its state is false, it will enter it, but before it executes the wait, if you broadcast it and then it goes to wait, it will go to sleep and wakes up.
Yeah, exactly. So, yeah, essentially like a lost wake-up scenario. So what might happen is if I don't have the mutex protecting isn't it equals to true, thread 2 could check the current value. It's false. So the next line it's going to execute is the wait. But before it executes wait, we context switch over to, say, thread 0. Thread 0 changes the value from false to true, then does the broadcast to wake everything up, and then thread 0 is on its way. Now, whenever we return back to thread 2, it will call cond wait, it will put itself to sleep, it will get blocked, and now nothing will ever wake it up again. It will just sit there and get blocked forever, so now we have lost thread 2. Data races are bad. All right, questions about that? All right. So, did we do this question? I think we did this one. Let's start with the UCLA exam unless, yeah, well, start with this. File systems, this section, we did the file system question, right? Yeah, we did it. So page replacement. You don't really need me for this, right? You can practice it yourself. It's probably going to be on it. All right, want to do this question? Threads? Looks like fun. All right.
Quick question about the PHP code replacements. Like when we're doing deploy PH1, do we have to like draw multiplier and also
Nope. Yeah.
just need to draw the
Yeah, whenever you answer, even if it's the clock, you just draw these because your clock's going to update every time. I don't want if no one's going to mark like all this in like 20 clocks or 10 clocks or however many. Yeah.
Do you have any tips for like not losing track of what you're doing? Like it's not a hard algorithm, but it's like you're gonna maybe lose track of where you are in a
Just like what I did in the lecture, like I went through it, I just drew my clock, and I just went through it each
Like
time.
if you keep erasing and like drawing and erasing with the hand
Yeah,
over and over again, your paper's gonna look like junk.
draw lightly. Light hand, light touch, and use a pencil. All right, so John writes an interesting web server that allows multiple clients to run the ls command on it. Wow, this is a cool server. I don't know why John did it, but he did. Maybe he was tired. Oh, right, yeah, I was actually late to class because I had to run and get my laptop, so that was fun. For the code example, assume no errors occur, system calls are successful. As a reminder, so this again was a closed book exam, so I told them some things that I will not tell you because you can bring your fun little cheat sheet. So, but this isn't much text. So as a reminder, the file descriptor returned from accept can be used in subsequent read and write system calls. So I didn't even tell them that much. So consider the following code. So we have a main, has a socket file descriptor, we set it up, does all that server stuff, setting up, doing the socket, bind, the listen, and then we have while true, except, so this, remember, is a blocking system call that will wait for a connection, and whenever it returns, you get a new file descriptor that represents that connection. If you write to it, you're sending bytes to whatever connected to you, and if you're reading, you're receiving information from it. So here I create a thread, and then I detach it, and I give it the file descriptor, and I do a little bit of some bad C practice where I cast an int to avoid star, and I just try and read it there. So now, right after a thread starts running, it calls sleep for 5 seconds, so this is what starts us off on our first question. So assume 4 clients connect, and each of them makes it to a call to sleep, and none have returned from sleep yet. How many threads are there in total, and where are they executing in the code? So accept returns 4 times.
Did you say like sockets are not on the exam?
I could ask like this about sockets. There's nothing, I wouldn't ask you like do all the setup stuff for it, do all that, but I could ask, they're just IPC. IPC is part of the course. So with this, what's the question? How many threads are there in total, and where are they currently executing? Yeah? 5. Where are they all?
4 of them are at sleep, and there's a main thread.
And what's the main thread doing?
It should be waiting.
Basically blocked by itself.
Yeah, it should be blocked by itself.
Yeah. So the answer to the first question is there's going to be 5 threads in total. So the current special main thread that starts executing main, well, it will be currently right here on the accept system call because it is blocking, it's waiting for connection number 5 to come in. So the main thread is currently there, and we have thread 1, thread 2, thread 3, and thread 4 all on the sleep line because, well, each time we have a connection that comes in, we get a new file descriptor. So say, I don't know, in this case it's file descriptor 3. Then we create a new thread, and we pass that file descriptor to that thread. So thread 1 would probably have file descriptor 3. It would read that into a local variable, and then call sleep. So 3, 4, 5, 6. All right. So okay for that, 5 threads in total. Main thread is in accept. The other 4 threads we created are in sleep. Yep.
So if a question asks how many threads are created, does it matter if you include the main thread? Like, because some questions ask, oh, you know, how many threads are created, and it gives the answer without the main thread. Would you like lose marks or anything?
If you make it explicit, you know what you are talking about. So usually when it says created, that's like not including the main thread. Usually the question will say not including the main thread or something like that, so I can get a consistent answer. But if the question doesn't say it, just give 2 answers, like here's the number. If you include the main thread, it's this. So either should be okay. Yep. So accept will block, and it will just wait for like someone to connect to the server. So as soon as someone connects to the server, then it will return a new file descriptor that I can like read and write bytes to. So it's just waiting for a connection like a web server or something like that.
So what's happening here is every time client connects, it goes through the while loop and then it goes blocks are set and then a client
Ye-
connects and then it goes again.
Yep. Yeah. So main executes, and then the first time through, the main thread will call accept, and then client 1 connects to it, so it returns a new file descriptor, and then that's how we talk to client 1, creates a new thread for that, sends it off on its way, calls accept again, and it would return a new file descriptor for client 2, and then we create a new thread for client 2, send it on its way, then it'll do the same thing for client 3 and then client 4.
Also, there's word 4 that are like existing.
Yeah, so it says assume 4 clients connect.
So the main thread runs bthread create, right? And then it goes to bthread detach. Is it but the thread is still sleeping, the creator thread is still sleeping. So how does it go about to accept?
So these are all, P threads are all kernel threads. So if all the other threads are currently asleep, the main thread can still run.
So maybe I forgot what the detach do. Doesn't detach have to wait for the sleeping thread?
No. So detach, all it does is eliminate the possibility of zombie threads. So as soon as this thread terminates, all of its resources are cleared out. I can't join it or anything like that. Yeah.
Isn't the detach analogous to wait PID but with no hang, so a non-blocking wait?
No.
Why would they be different?
So detached, as soon as that thread terminates, it's all cleaned up. For processes, there's no equivalent of detached because someone has to wait on you all the time.
But if you could join, would the get cleaned up as well?
Non-blocking.
Yeah, so there's like wait with no hang, that's a non-blocking check. For thread join, it's always blocking. There's no non-blocking version of it. Another one somewhere? Okay, it was covered. All right, so what's the next question? So now all threads return from sleep and complete what gets sent over the socket and why. All right, so now we have to continue reading. So now each thread calls fork. That's fun. So each thread calls fork. Remember what happens when each thread calls fork? Yeah, so new process gets created and it's a clone of whatever the thread is that called it. So the new process that gets created is not going to have 4 threads in it, it's only going to have 1. So, for example, if we started off in, I don't know, process 100, then thread 1 would make process 101, thread 2 would make process 102, thread 3 would make process 103, thread 4 would make process 104. So they all create a new process, and then I check if PID is equal to 0. So what does that mean if fork returns a PID of 0? Yeah, it means this is the child process. So, yep.
I just want to ask, like, so when you fork a thread, you get a copy of the thread. So would it count as like another thread that you create?
Yeah, so the new processes by default have one thread in them. And usually we call it the main thread if it just started normally. But in this case, yeah, the one thread in the process would be a clone. In process 101's case, it would be a clone of thread 1. Alrighty, so now we check in the child, we do a dup2. So whatever that file descriptor is we got that represents a connection, we make file descriptor 1 point to the same thing, and then we call exec lp to execute ls. What does exec ve or exec lp or any of the exec system calls do? Yeah, we essentially reuse this current process, so process 101 becomes ls, starts executing ls things. So in that case, all the output of ls would be sent to file descriptor 1 by default because it would use standard out. Where would that information go? Yeah, well, file descriptor 1, what's file descriptor 1 pointing at? FD, no, specifically in this case, what's file descriptor 1 pointing to? The socket. The socket. So we would be sending the output of ls across the socket, and it's essentially like doing this is essentially a very scuffed version of SSH. Because you're running commands on a different machine than what you connected to. Yeah.
But like, okay, so we're taking the output of ls and we're shooting it through the socket. But like, what's the point? It's just you didn't write ls something, so like, wouldn't it just give you a really like weird output?
No, ls with no arguments shows you the contents of the directory.
Well, the directory the laptop is currently in.
The directory this process is currently in.
The directory the process that called it over the server.
That is running the server.
Well, why would it?
So process 101 would be running on the server, and it would have been running in some directory. So ls by default would just show you the contents of the current directory.
But like, if you're using a socket, wouldn't you want it to show the current directory of the server and not your own?
Yeah, this is the current directory of the server because this is running on the server. This is the server code. This is only the server code. There's no client code here.
Oh,
Yeah.
wait, I'm getting tripped up by the do again. Just like ls by default prints to
File descriptor 1.
so then you're telling it, oh, prints like whatever empty is that that's connected to the
Yeah, so let us take a little detour, I guess. So in process 101, well, right before it, they would have file descriptor, here, I'll write it to the side. It would have file descriptor 0, 1, 2, and in this case 3. And then there would be like this local open file table. So it would have, you know, its position. What else is in there? Position, someone help?
User data permission? No.
Position, oh yeah, permissions, and then a vnode. So it would have this for all of the current open file descriptors. And then we would have like the global open file table, or sorry, the file descriptors are like the local open file table, and those are the global entries. So I wrote it backwards. All right, so it would look something like this. And then, you know, that vnode would probably, for file descriptor 3, point to the actual socket connection, or maybe I'll just call it connection instead. So if I do a dup2, what that means is it's going to take whatever this file descriptor is pointing to and also make file descriptor 1 point to it. So that dup2 system call will essentially change this in the local open file table such that file descriptor 1 also points to that same entry. And since it points to that same entry, now if that process does a write to file descriptor 1, it's going to actually go to over the socket, over that connection. Yeah.
If I seek the position, then it would change for both the file descriptors, right?
Yes. Yeah, in this case, because all the file descriptors are shared in all of the processes, if you got that file descriptor number and you LSeeked, because it would only have entries in the global table, it would change the position for all of them. Be kind of rude. Yeah.
Doesn't group 2 also close the old script?
No. So dupe 2 will, oh yeah, so dupe 2 will close this one if it's not closed already, but that's part of changing it to the other one. So technically, if I wanted to slow it down, it would have deleted entry 1 first, like just got rid of it, and then, well, now it's available to point to something else, so it could make file descriptor 1 now. So if you want to think of it that way, but probably easier just to think of it just swapping or changing what it points to. All right. So with that, so now, what gets sent back over the socket and why? So the server will send over the socket the contents of running ls on this machine. So it's essentially SSH, because you are running commands on a server somewhere else that is not your local machine. So your machine would be the one that, calls connect or whatever, and then the server accepts it, and then it runs commands on the server. All right, so any questions about 2B? Or not 2B? Yeah. God, I'm terrible. All right, how many processes did we create excluding the original running processes? So in this case, we wrote it before. We have 4 newly created processes because each of the threads will create a new process, so 4. So any problems with that? All right, so wow, I have a typo here. That's embarrassing. So what did we forget to do with the newly created processes? Why is this especially an issue in this case where a server runs for a very long time? So whenever you create processes, you should probably think, am I being a good parent? So in this, is this a good parent? No. So process, in this case, process 100, if that's the original process, all of these would be children, right? So all of these would be children. All of the children just run ls and then finish. And whenever they finish, what is, let's say process 101 terminates, what is the current state of process 101? Yeah, it is a zombie, right? And we don't like zombies because they're wasting resources. So in this case, I could create up to 4 zombies because I have 4 connections. If I have 10,000 connections that happen, how many zombies do I have? 10,000, which probably starts being bad. If I have 1 million, how many zombies do I have? 1 million. Okay, now I probably have actually run into an issue. I will eventually run out of memory and then crash. And this is like the common solution to some poorly written software is, yeah, just restart the service and it'll work again. No problem. Probably because of an issue like that. So, any questions about that? Yep.
Since like this case you have like a server where like the original parent process would like terminate until like the end of the service, so you wouldn't create any orphans, or would you create orphans?
Yeah, so in this case, do I create an orphan? Yeah.
No, because your main thread is just stuck there and it's going to be alive.
Yeah, in this case, assuming that I don't kill that process for whatever reason, if it just runs normally and it's in an infinite while loop, it's just waiting for connections, it'll run forever, so I won't have any orphans until, well, maybe this process has created too many zombies and we have to kill it or something like that, and then it would create a bunch of zombie orphans and then they'd all get cleaned up. Yeah.
So to fix that problem, you would just wait right after the safe run.
Yeah, wait, so I could just do like a wait PID here, wait on PID. Right, now we don't create any zombies, we're probably good now. All right, so what was that? Yeah, so we didn't call wait on them, create a bunch of zombies. So they're not going to become orphans, they're not going to get reparented, they're just going to stay zombies for as long as the server's running. Eventually, we're going to run out of resources.
For the wait pit, you can't have like no hang for this, right? Or else it wouldn't be useful.
Yeah, if you have no hang on the wait PID, well, you might call it and then that process is still running and then it's like it's still running and then your thread terminates and it's never going to call wait PID on it.
So in
Yeah.
this case, they should be blocking. They should be blocking.
Yeah, in this case, it would make sense to be blocking. Yep.
In the code, could you know why orphans won't be created? Because we do return null if the PID is not equal to 0. So wouldn't we return?
So this return null, this is the end of like thread 1 running, thread 2 running. So this would eventually call pthread exit. And that would end the thread that got created here. So it just ends the thread. So thread 1 will be gone, and because it was detached, it won't be a zombie thread, so it'll just clean itself up. But all the other threads, including the main thread, are still running. If instead of just implicitly having a pthread exit, if I just straight up called exit, then I exit the process, all the threads are now gone, and well, I don't have any issues anymore because this process doesn't exist. All right, so now, what would happen if we did not fork and instead always executed dupe2 followed by exec directly after sleep in every thread? So in this case, what it is saying is, let's see. So instead of the situation we had, I don't have this line, I don't have this line, and I don't have anything like that. Yep.
Since the threads are created for like the process, if you use exec LP, you'll like end the process itself and then start a new one. So it wouldn't work.
Yeah, so in this case, what's going to happen, let's say I've, again, 4 threads that connect to it, and they all start running this run, they're all set up to run it. Well, one of them is eventually going to execute, let's say thread 2. Wow, that's gigantic. So thread 2 would get its file descriptor sleep for 5 seconds, then call dupe2, and again, remember it's running as process 100, so it would just change process as 100, file descriptor 1 to point to its socket, then it would exec LP, and then process 100 would be replaced with LS. And now the server is not running anymore, so we would just, whatever first made it there, we'd send that information back, and then for every other thread, they'd just be wiped off the face of the planet. Yep.
So what if instead of forking inside the thread, we just forked inside the while loop instead of creating more threads, we just created children? And of course, like instead of detached, we waited on them with no hang. Would that also be okay?
So if instead of this whole terrible thread thing, I just kind of delete this and then essentially take this and move it here.
Yeah,
All right, is that bad, anyone?
probably bad. It slow things down a lot. But
Yeah. So if I move it, well, then I essentially only have one thread executing. As soon as we get a connection, well, it would make a child. And in this case, assume I have my wait because I don't create any zombies, don't create any zombies. Well, it will create a new process, wait for it to finish running, and essentially I can only handle one connection at a time. So I'm going to have to accept the connection, wait for it to finish completely before I start another one, and I can only do one thing in parallel at a time. It's going to be really slow. Yeah.
You should be able to do this process only thing. If you were to create, like you can run, like processes can run currently as well.
Yeah, so the problem is since this wait PID,
Yeah, so
Yeah, if I want to make it and I get rid of wait PID, well, then technically I could go through the while loop and have like a while loop that pulls and does like a no hang.
Like you have like a signal handler that kills the child, or
Yeah, or you could have a signal handler or something like that, so that would work fine.
a better approach, right? It is like this question is just for the sake of asking about threads and processes, but like in reality, if you were to make this, you probably wouldn't use threads.
In reality, the thread probably does a bunch of other stuff that's local that might run for longer, so it would probably be better to use threads. But in this particular example, that's kind of silly. Just processes would be fine if you had a signal handler or something like that. Yeah.
I mean, like using threads in this particular situation, you still can like use concurrency, you know, like really, really well if you use threads because accept is blocking, no.
Yeah.
But that's only if you had a uniprocessor machine that would work well, or even if you have a multi-core machine, using threads in this situation would be good.
No, it doesn't matter because the operating system's going to schedule processes instead of threads. It's going to essentially be the same thing. Yeah.
So when you when the detached pthread goes into its one function, it calls pthread exit on the return, right?
Yeah, so whenever we give a function here. Whenever this returns, it will implicitly call pthread exit just like you did in lab 3 or lab 4.
That's the case for the detached and non.
Yep. Yeah, it doesn't matter what type of thread it is. It's just always going to call exit whenever it's done its function.
Okay, and the only difference is that the non-detached one will have to like.
Yeah, the only difference is the other thread, so it's either going to be detached or a joinable thread.
Okay.
If it's a joinable thread, then the rules are like with processes, I have to call join on it, which is essentially equivalent like wait. Yeah. Oh, no. All right. All right. If I was a, oh, let's see what the, yeah, there's one last question. So if I was a betting, yeah, what would be the issue if we removed pthread detached? So now, yeah, so if I remove that, now I have zombie threads. So they finish executing, they call pthread exit, and then, well, I don't call join on them, so essentially they're wasting some resources. So I could have zombie threads and zombie processes at the same time and have a whole zombie party. Ooh.
So pthread detach implicitly calls pthread join. Oh,
No, pthread detached does not implicitly call join. If you want it, you can think of it kind of like that, except it just trashes the return value because part of join, you get the return value out of it. So if you,
it does the same thing essentially.
yeah, it essentially does the same thing where it cleans up all the resources. So if you want to think of it that way, where it just automatically joins and trash, and you just never see the return value.
And unblock it.
Yeah, yeah.
The RPC thread join here, where would we put it?
Exactly. If we were to use pthread join here, where would we put it? Yeah, it'd be pretty bad. So this would be an example where detached is actually a good thing because I don't care about the return value, and placing join would be a pain. So this is a case where detach is actually a good thing. All right, so now we got, all right. Oh, this looks, do we do locks or do we move on? All right, let's try and do it in like 7 minutes. So transfer function, so this looks kind of similar to the bank thing we did in the lecture for the parallelization example. So we have a struct called account that has 3 fields. It's got a mutex, a name, and an amount. Then we have our fund transfer function that, oh, that's smart. It checks if we're transferring to and from the same account. If not, it just returns. Otherwise, we lock the to mutex, and then we have a deduct function. In deduct, we lock the other account. Here, I will make the threads a different color. So in both of them, all the deduct does is check if the amount is able to be deducted, and then, well, it subtracts that amount and then returns the amount it actually deducted. And if there's not enough money, it just sets the amount to 0. And then in the transfer, we just add that to the to account. So in part 5, does this code have any data races? Come up with an example of a data race or justify why it does not. Yeah.
It should have a data race because, like, if say account you're transferring from account 1 to 2, so you would lock like the 1, and then when you call it deduct, you want to lock 2. But if there's another thread or something that calls lock from like 2 to 3, it would lock 2, and then you or sorry, it would lock from you're transferring from 2 to 1, and when you call it, it would be like a circular way.
So circular wait is not a,
Circular way. I forgot what the term was, but it's
well, circular wait is not a data race, right? It's a deadlock.
what was the question?
So this question, does this code have any data races?
Okay.
So we answered a different question. So this case does not have a data race because, well, should remember data race, 2 concurrent accesses to the same location, at least one of them is a write. So the to mutex is protecting the reads and writes to this location, so 2's amount, and then in deduct, well, we're protecting concurrent accesses, which are here to the from accounts amount here. So we're not trying to access anything from the to account in the deduct method and vice versa. So we always are only changing the amount of a account with its associated mutex. So only one thread doing concurrent accesses at a time. So while there's only one thread, there's no concurrent accesses. Doesn't matter if I'm reading or writing. If there's only one thread able to do it at one particular time, we have no data races.
Wait, sorry, hold on. So you're changing the 2 amounts in between the blue,
Yep.
and you're not changing the 2 amount in the thing. In the green, you're only changing the.
Yeah, so here, with this particular call right here, I'm only changing the to amount. And then within the green, I only change from because, well, from is always equal to that.
Yeah, so there's no data race.
Yep, so no data races in this case. All right, next question is, yeah, does this have any deadlocks? Sure does. So, has a deadlock, so assume, we have a transfer from A to B, and then a transfer from B to A. Well, in that case, we could have thread 1 executing this, thread 2 executing this. So thread 1 could go ahead, acquire lock A, and now it has lock A. We context switch over to thread 2. Now it executes, it acquires lock B, and now we are screwed because neither of those 2 threads can make any progress anymore. Thread 1 wants to get lock B, held by thread 2. Thread 2 wants to get lock A, held by thread 1, so we have a deadlock. All right, the next one is, given the issues you found in 3A and 3B, explain how you would fix this code to prevent these issues. You may not significantly refactor the code. That means that transfer must add to the transfer must add to the account and call deduct. Also, deduct must safely decrement the account only if it won't have a negative amount, otherwise it must be 0. Deduct always returns the amount deducted. You may write a replacement function or explain yourself clearly. So, how would I change this to get rid of the deadlock, since that is our issue? Yeah.
I'm not sure if you have moot points for this, but couldn't you just use a single mutex and call it a day?
Single mutex and call it a day?
You'd probably lose points to the,
You'd prevent a deadlock,
but you're going serial.
but yeah, then you'd be going serial, and that probably would count as significantly changing this program. No, tri-lock's not significantly changing. So yeah, is that going to be your? Yeah, so just use a tri-lock. So in here, that's what I do. Keep deduct the same. Well, actually, I could just move the code around in this case. So I don't even have to do a tri-lock. In fact, this was actually trying to prevent you from doing a tri-lock because adding an argument, so I could give up the first lock would be refactoring it. So in this case, I could actually just call deduct outside of this and then go ahead and actually adjust the to account in a different thread, or yeah, with its locks. So I just move it so it looks like this. So I call deduct without any locks, and then I do the lock to 2 only after I'm done with deduct, so now I'm only holding one lock at a time, so I don't have any deadlock conditions. All right, so we are done. Oh crap, I'm over time. Oh, I can't even play the song anymore. Ah, crap.
So if you did tri-lock, would that be bad? Like,
Sorry?
like would you not be able to do a tri-lock? You can.
You can't do a tri-lock because you don't have access to the other lock. All right, just remember pulling for you. We're on this together, and then yeah, there we go. All right, you can leave.